USB loudspeaker, Mr. Bob Beck, telling us about Unveil. No pledge?
No, it's just Unveil.
Just Unveil. Go ahead, enjoy.
So I'm Bob. I'm here to talk to you about Unveil, which is a new thing in OpenBSD, this upcoming release.
I know it's a mistake, but I'm giving you a mistake.
The stick is kaput. I broke it.
If you need to get anything broken, Bob is there.
Yes, I'll tell a story at the end of the time. So what's Unveil? Unveil is very simple. It is to unveil parts of a restricted file system view. What file system view, you might ask? Well, you call it with Unveil, you give it a path, and you give it some permissions. And with the first Unveil call, that's your restricted file system view. The only thing that your program can then see when it looks up names in the file system after that call is the path you gave it, certain broad parameters. You might say, well, why would I know one path? Well, the first call to Unveil restricts the file system to what you have. And future calls to Unveil are special. They're allowed to continue to unrestrict the file system. So access to a path that is not unveiled returns enoent. So if you unveil Etsy hosts, great. Your program can open up Etsy hosts and do stuff with it. If you then try to get at Etsy password, you'll see enoent, like it didn't exist at all. Okay? The flags actually control what permissions, what things are allowed to be done with what you've unveiled. So you can actually have this little more fine-grained control of whether the file exists or not based on what you're trying to do to it. So it's similar to file system permissions. It's RWX, which you might be familiar with, and C, which one we added. So read is for read operations, write is for write operations, X is for execution operations, and C is for creation, so creation and deletion. Okay. This kind of roughly corresponds to how pledge deals with things, but it is dealt with differently in Unveil. Okay. The first call to Unveil, as I said, restricts the file system view. Calls after it can open it up more until you make a special call. So when you're done opening up the file system, you have the restrictions the way you want them, you call unveil null null. And unveil null null means your program is not allowed to call that system call ever again. It will just fail. The alternative is there is some pledge integration. There's a new pledge called Unveil. And if you pledge without the Unveil, then it's not only will you, with Unveil null null, future calls to Unveil fail. If you drop pledge and drop Unveil, it's like pledge, future calls to Unveil your program will get shot again. So that's kind of what it is. That's kind of neat. And so the first thing to notice is it's kind of similar to other things we've done. File system sandboxing itself isn't very new. Chroot is, the first example of this you've probably seen in Unix. It's been around for ages and ages. And it's, I'll restrict the file system by making a chroot. And I will put this program into the chroot, and I'll put what the program needs into the chroot, and hopefully not have stuff in there that lets the program escape the chroot if we're optimistic and careful. And if we're in the typical chroot, we put everything in the kitchen sink inside the chroot, and anybody competent can often escape the chroot. What's the other problem with using chroot in your program? Anybody know? What?
You need everything that you want to use in the chroot.
Okay, what else do you need in order to use chroot though?
Root.
You need root, right? Hey, I got root. So right away, if I'm going to chroot the program, I have to start it as root. So immediately I need some extra privileges just to then restrict it later on. And hopefully then I can drop privileges after the fact, but it does mean your program needs to be special. There are other ways to do this. There's jails, there's Capsicum, there's Linux, various and sundry ways to do it in Linux. The trouble with a lot of these is they tend to be externally set over the lifetime of the program. And if you think about a program and what a program accesses accesses and does, you've seen this as, programs tend to do a lot of things, particularly when they start up. At least if you are not in the, I'm going to turn everything into MS-DOS unikernel because I don't understand shared libraries. When you have shared libraries, you have a vast array of .SOs, you have LD.SO. When your program starts up, it accesses a lot of the file system. It does a lot of things. And so if you're going to restrict the file system and yet still be able to invoke your program, you probably need to have all of that shared library infrastructure in there. Something you might not typically want for the rest of the life of the program. A lot of programs will have to go and read configuration files and all sorts of fun things and private keys and good stuff when they start up. But when they're actually doing their work and interacting with other things, they don't need these things again. Okay? And that's where it comes, well, you have to externally set the program. You have to give the program everything it needs over its whole lifetime, which might be more than you would do if you want to actually just have it restricted where it's actually exposed to something you don't want it to be exposed to, like talking to the internet. So we want the programmer to be able to choose where they restrict it, and the goal is to actually have tighter restrictions in the important part of the program, i.e. not the startup where I haven't even opened a socket and started talking to the internet yet. I'm probably, chances are I'm not going to be attacked there. I'm going to be attacked when I'm talking to the internet and reading garbage off the internet, and people are, sending me all sorts of things, trying to make my string parsing break, or sending me all sorts of hostile payloads, or I'm just loading JavaScript and running it because that's what browsers do. So it's intended to be a little different than Chroot and the friends of it. So it is actually meant for use by developers during development, not by system administrators or system partners after the fact. It is meant to be, oh, I know what my program does. I'm going to use this to say, hey, this is what my program is going to do. So it's kind of like Pledge in that it follows the model of, hey, I'm going to manipulate what I see at runtime. Okay? Because, and if you remember with Pledge, it's the same thing. Hey, I promise my program is only going to do these behaviors. And if it doesn't, we shoot it in the head. And this is a little bit different though. Pledge kind of has a small set of semantics to control, which sounds odd because Pledge is kind of complicated. And there's a lot of corner cases in the kernel to implement Pledge. But if you think about Pledge from a user's point of view, it's pretty straightforward. Hey, I promise that my program is only going to do read operations in the file system. And the semantics are really clear. If you do read operations in the file system, it works. If you don't do read operations, if you do something that's not a read operation in the file system, what happens to your program with Pledge? It's simple. It dies. It instantly dies. So the nice part about that is it's safe. It's very, very safe, okay? Because if your program does something it's not supposed to do, it doesn't get to execute any more code. It doesn't do weird things because it did something it wasn't supposed to do. It just fails, okay? But file systems have interesting semantics. Oh, my slide's cut off the bottom. Sorry, bad projector. libc used files, as we mentioned, ld.so. Per program known files, so hey, this particular program opens its own configuration file and needs to reopen it, or it doesn't need to reopen it later. Particularly if it, opens it up and puts it in memory, keeps it around, or if it needs to reread it. Files provided by argv or configuration. Well, if a file is provided by argv or configuration, who knows where that file could be, right? Could be anywhere. File names that a program just knows, they're hard-coded into it. Oftentimes, Unix programs treat things specially if they're in your home directory because $home gets read, and that's how it knows where your home directory it is, and it magically looks for things there. And the interesting one comes into lots of times people on Unix, even inside programs themselves or in configuration directories, love to make symbolic link trees. They like to make a giant forest of symbolic links from, oh, well, my thing is here, but I'm going to make it over here because I like to start it called with friend or .glib. And I can't have the configuration called home Beck. I have to have it called, relative glib configuration, which is symbolic links to some other damn place. So, great fun. So, this gets down to how we made it, and this was a long slog, actually. Unveil semantics are a big compromise between two objectives. We want as near to order one behavior in the kernel for the worst case program installing the worst case rule set. And when I say order one behavior in the kernel, when lookups are happening and programs are running. We don't want a program that installs deliberately a horrific Unveil rule set to slow down the system for other people. Okay? And that was one of the big challenges doing this, because of the way main lookups happen in the kernel and where they happen in the kernel. And we also want semantics a programmer can comprehend. As we've seen with Pledge is relatively easy for a programmer to comprehend. That's why we have lots and lots of the OpenBSD base is pledged. And it doesn't try to do things that have crazy, crazy options that people can't quite get their head around. So doing this required substantial kernel object storage and tracking and checking to make it as efficient as possible. So after a few discarded designs, and by a few discarded designs, I think I mean 3 disrupted ports hackathons. It always seemed to happen at the ports hackathon. Everybody would show up for ports, and Theo and I would sit in the corner and argue with Samarie and go bashing back and forth on what we would do for this. And it was originally called Pledge Path, and was thought to be part of Pledge. And as we got onto it, it's like, no, this doesn't belong in Pledge. It is different. It is a new system call, and it's not the same thing. So we ended up doing is there's a per process structure on every process that holds and remembers directory vnodes, only directory vnodes that are looked up at the time of the Unveil call. Unveil in a non-directory remembers the name underneath its directory vnode. So if I want to unveil etc password, what's held in the kernel is the vnode for the directory etc, and name, password, in that structure underneath there. It's a sorted list of vnodes with a red-black tree of names underneath it. Is actually what ends up being stored in the kernel. So I can do the name lookup quickly, and I can find the vnode quickly. What's the sorted list of vnodes? It's by the same way the kernel always keeps track of vnodes, by address. It is sorted in order of pointer. Vnodes have some interesting properties, particularly how they're held and recycled. So non-directories can be removed and recreated after Unveil. And this was necessary. Initially we thought, hey, we'll just hold the vnodes for everything. Great. You can't change and recreate a file. If you unveil it, the file had better stay there, or you can't see it again. Why is that? If you remove a file and recreate it, it gets a different vnode, right? If you remove a directory and recreate it, it gets a different vnode inside the kernel for every time you do that. And the trouble with that is that, okay, it was probably reasonable to keep the directory vnodes because you don't typically rototill your directory structure during the life of a program. But it's really, really common in a program to say, oh, I'm going to change my configuration file and I want it to happen atomically. So I don't want to start a write, because I just happen to have 80 megabytes of HTTP or Nginx configuration, and I'm going to write that all out sequentially, and I'm worried that somebody's going to notice and read it halfway through me writing it out and have bad things happen. So what we typically do when we replace a configuration file is we write the new one and we switch them atomically with Unveil, which means, hey, a new file is created on that same name. It's a different vnode. So if you just held the vnode for a file name, that isn't going to work. You basically put yourself in a situation where you can't do that. So, okay, we'll remember the name underneath the directory. As long as you look up and open up the correct name under that directory, it's all good. Directory vnodes, they cut off the bottom, can't be directories once unveiled. If you move or change the directory, no, it's going to forget about it. Unveil won't know. If you do it between the time your program unveils it and the time you use it, it won't see it.
So for log file rotation, because I'm getting a new file name as well, so I can just unveil the directory.
Okay. You can also unveil just the directory. And if you unveil a directory, it's good for any operations within that directory. So the normal thing, if you're going to have new things, just unveil varlog, because you're scribbling shit into varlog. And then you can do whatever you want in varlog. So, Unveil can affect program behavior. And this is where it's really, really different from Pledge in a kind of a scary way. And again, in Pledge, If your program breaks the pledge that it has made, it's a boom, kernel shoots it in the head. It's dead. It's easy, straightforward, it's clean. And death is wonderful. The problem is your program may not die nicely if things happen in the file system that it's not expected to happen. Programs can do interesting behaviors. So unlike with pledge, where you know as soon as the pledge is broken that the program isn't running anymore, with this, you decide to say, hey, that file doesn't exist, or permission denied, and the program is going to keep running. Hopefully it's going to do the right thing. Sometimes they do interesting things. Part of this, as we went on, initially I returned the EuroBSD for everything. It's like, screw that, EuroBSD, it doesn't exist. Unveil, the file system is gone other than that. But when we added permission flags, you kind of notice that a lot of programs take a different error path if they're paying attention to error node, when they do system calls and do reads and writes. And they do different things when I open it and say permission denied, as opposed to I open it and it says no, it doesn't exist. Okay? And so, generally speaking, if we've unveiled something for read only, and we try to write to it, the programs seem to usually take a better error path if we actually say permission denied, rather than that file didn't exist at all. Okay? But, well, you know, as we'll see, there can be a few different things. So, we started working on this with it in the kernel and a bag of small programs in OpenBSD base. So there was, you know, Bob with a big chunk of horrific vnode diff from the kernel, and Theo with a big chunk of userland programs tossing a big diff around, and this went on for months and months and months. What we did is, there was some integration with pledge, a special bit for Unveil. The initial unveils of small OpenBSD programs look really, really nice, with just these basic semantics of I'm going to hold a vnode, I'm going to remember what you looked up. When you look up a file name, you get EuroBSD or eAccess, depending on what you're doing if there's a problem. So, for look just up here. Anyway, ActiveClient. ActiveClient was pledged, but ActiveClient also has an Unveil in it, which is kind of nice. So, even though ActiveClient has two processes, it's privilege separated. There's a network process that talks to the network, and there's a file process that does the scribbling and handling of files in the web directory. Okay? And so what you end up having is you have the default CA file is the only thing that the network process can access. So it's still pledged read, but that in of itself lets it read anywhere in the file system. The Unveil also says, well, not only are you pledged read, but the only file you're going to be able to read in the file system is default CA file. Okay? Which is the thing you're going to use to validate the certificate when you go talk to your Acme provider to go get a certificate. Meanwhile, the file process, which actually goes and scribbles in the challenge file and then scribbles the certificate you get returned back, well, it's unveiled to be able to just read, write, create in the certificate directory. So it can read, write, and create files, can't execute anything, but it's the only part of the file system it's going to be able to see. And so the idea is we can use this, and even though this one's actually pledged, we can actually use this to restrict programs that aren't easily pledgeable or further contain those that do. And like pledge, it kind of makes privilege separated programs a little better. If you've decided you've privilege separated a program, it has components with different functions that touch different pieces of the system with different privilege. You can use this to actually better articulate that. You know, you designed it such that, oh, this is only going to do this is only going to do that. Well, this actually makes the operating system enforce it, just like pledge does in terms of the system calls. This kind of does that for the file system. So basic use of Unveil. If you look at the users command in OpenBSD, users is really stupid, by the way. What does users do? Anybody ever used it? Anybody remember it? It's really old school. You type users, and it tells you who's logged in to the local system by reading the utemp file. So it's pretty dumb. It just parses crap out of the utemp file and says, yeah, Beck is logged in on TTYP0. Okay? And what it does is, if you look at it, this is similar to what you usually see. Hey, Unveil. Hey, the only thing that thing should be able to do is look at utemp. So all we do is we let it read utemp. And if Unveil doesn't work with And then guess what? We immediately also pledge, because this is a common theme we see throughout OpenBSD base. Hey, I did an unveil, and then I pledged. So I'm only going to do read operations in the file system based on the pledge and talk to standard I/O so I can spit out Beck is logged in on TTYP0, and I'm going to read the utemp file to find that out. And then I parse my options and do all the things the program is going to do. Okay? Now, you notice here there's no unveil null null, even though I said you can do unveil null null. And actually, almost any program in OpenBSD where we use pledge, we just use pledge and not null, unveil null null. Because you know this pledge doesn't say unveil it. And any pledge, that's the set of pledges. So after that point, I can't call unveil anyway. I will have a pledge violation, and I'll get shot if I try to call unveil again to open up the file system further. And it is important to stop unveils, because otherwise, well, the program could just call unveil and unveil what it wanted after the fact. So it's a little different than pledge, where you start with a set and only restrict it. Unveil, you keep unrestricting yourself until you say stop. Don't let me unrestrict it anymore. Less basic use of unveil. OpenBSD's NC is a network Swiss Army knife. If you've used NC and you looked at the man page for NC, it has an alphabet soup of options. If you can find the letter in a bowl of soup, there's an excellent chance it's an argument to netcat. Blades are chosen based on the alphabet soup command lines. And if you look at this, this is a complicated one, where, if I'm using TLS, and if I have the C flag says that's for certificate, the K flag is for key, the R flag is for, I forget, I should know I maintain it. O flag is for OCSP options, an OCSP staple, because everybody's netcat should be able to, in a server mode, support OCSP stapling to say whether the certificate that you're using for netcat is revoked or not. It's true. And we support that. And if we're not using TLS and we're using Unix domain sockets, unveil and allow yourself to open a Unix domain socket in whatever directory you've chosen to scribble the Unix domain socket into, which is temp by default. And otherwise it's provided by the S flag. And otherwise just unveil / for nothing. So there's a different unveil for many blades of the knife. And this is immediately followed by a block that does, similarly to most different blades of the knife, just to show you that it's all kind of related. We do all our unveils based on what option we're doing. And then, hey, we do a whole bunch of pledges. And we do a different pledge based on whatever option we're doing. So, if I actually have to do Unix domain sockets, I need a whole lot of pledge because I'm doing a whole lot of strictly's. And if I'm just doing plain old TCP, I'm just doing standard I/O, INET, and DNS, and a bunch of varieties in between. So there's a different pledge for each blade of the knife. And the result is it's harder to usefully compromise it if it's yakking at something on the internet and somebody manages to find a vulnerability in it. So, then it got fun. So we had about